Hello, my name is Alexander Mook from the University of Basel, and I'm going to talk about the damping of skyrmion crystal eigenmodes in the quantum limit, in which the eigenexcitations can decay spontaneously even at zero temperature. This work was carried out at the University of Basel in Switzerland in the group of Professor Daniel Loss, where I'm working as a postdoc, and also in collaboration with the group of Professor Jelena Klinovaya. We are interested in the eigenexcitations of skyrmion crystals mainly because we have in mind to realize the paradigm of magnonics, the idea being to replace the charge degree of freedom of electrons with the spin degree of freedom, and then to replace electrons altogether because the excitations of magnetically ordered materials, the magnons, can also carry spin, and since magnons don't carry charge, information processing with magnons is associated with a much lower waste energy production. In particular, there has been one material class that has drawn a lot of attention over the recent years, the so-called topological Magnon insulators. These are materials that come either in the form of magnonic crystals or as atomistic materials, but they have in common that the magnonic spectrum of these materials exhibits a gap within which you find a mode that is localized to the edges of the material, and it comes with a given group velocity, which means that if you locally excite at this given frequency this material, you excite a magnon or spin wave that unidirectionally revolves about the sample. And this is very much reminiscent of the electronic chiral edge states in quantum Hall materials, where you would also find, if you look in reciprocal space, a metallic state that connects the insulating gap between the valence and conduction band. And this chiral state is also strongly localized to the edges of the material, with the classical picture being that it is a skipping orbit. Interestingly, you not only find these excitations in two-dimensional materials where the excitations go around the edges, but also in 3 dimensions where the chiral state goes around the hinges of the material. But here I will focus on the 2-dimensional realization. And this is then also the point where the skyrmion crystals enter, because these non-trivial winding of the skyrmion crystals generates emergent electrodynamic fields, in particular an emergent magnetic field, that forces also the magnons, not only electrons, to condense in Landau levels, which is why the magnonic spectrum of these materials exhibits rather flat magnon bands. And it turns out that due to this non-trivial winding of the texture, not only the texture on real space is topologically non-trivial, but also the magnonic bands, as characterized here by topological invariance, the so-called Chern number. And the non-trivial Chern number then tells you that there has to exist such an edge state that connects two adjacent bulk bands, such that at a particular frequency you find magnons or spin wave excitations that go around the skyrmion crystal unidirectionally. Now, this interesting topology at the single particle level is brought about by the non-trivial winding. However, the non-trivial winding, or in particular the non-collinearity of the texture, also brings about 3 magnon interactions or non-linearities and harmonicities that can cause spontaneous quasiparticle decay. Let me give you a quick introduction to this phenomenon. The situation is as follows. We have a spin Hamiltonian with a magnetically ordered ground state about which we can expand the spins in terms of bosons, such that we have a ground state energy, then a harmonic theory covered by H2, and then higher order bosonic terms. In particular, there are 3 magnon interactions where a magnon can be spontaneously destroyed with 2 other magnons being created. And it doesn't take any thermal energy for this process to happen, which is why we speak of spontaneous quasiparticle decay. Such a phenomenon is known, for example, from the phonons in liquid helium, or for as quantum excitations in some quantum magnets. And typically you would find in neutron scattering that there is a well-defined, rather sharp quasiparticle feature, which suddenly ceases to exist because the spontaneous decay is so large that the quasi-particle weight is almost completely wiped out. You also see it here. And now the question arises whether the interesting single particle topology of the magnonic bands and skyrmion crystals actually survives this kind of many-body interaction, given that it is brought about by the same mechanism that also brings about the interesting topology to begin with. And to answer this question, we have been conducting a numerical study based on the simplest two-dimensional model with which to realize a skyrmion crystal. We consider this spin lattice Hamiltonian with ferromagnetic nearest neighbor exchange and Zielinski-Moria interaction, here chosen as interfacial DMI that would stabilize Néel skyrmions in a particular range of out-of-plane magnetic field, as you can see here in this sketch of a phase diagram. And we now expand about this ground state. We can calculate the harmonic spectrum of magnons, but in particular, we are interested in these processes where one magnon comes in and spontaneously decays into two others. First, however, let us have a look at the harmonic spectrum of skyrmion crystals, where you can see here the rather flat Landau level-like magnons. And each of these bands at the gamma point at least corresponds to one of the typical skyrmion modes. So for example, you find these polygon-like deformations where you see an elliptical deformation, triangular or higher order deformation. But you also find the three magnetically active modes that can be measured by microwave absorption experiments. You see the anti-clockwise mode, the breathing mode, and the clockwise mode. Now, the damping of these modes can be calculated within many-body perturbation theory, where you consider many-body interactions as a perturbation to the harmonic theory. Within lowest order in H3, if you're only interested in the damping, this condenses into Fermi's golden rule, where the damping of the nth mode is given as a sum over all decay channels for the nth mode to decay into two other modes, given that this process conserves momentum and energy. You see here that the damping is determined by two contributions. One that is kinematic in nature, that tells you whether or not a particular decay channel conserves energy, and the other contribution that is dynamic in nature, that tells you about the interaction vertex for a particular process, which tells you something about the efficiency of the decays. If we forget about the dynamic part for a second, just assume that it is constant and finite, then we see that the damping is directly proportional to the two Magnon density of states, where you just sum over all combinations to add two single particle energies to end up at a particular momentum and a given energy. So let us have a look at that. Here again, we see the single Magnon excitations, which are reproduced here by the white lines. And in the background, you see the two Magnon density of states, with blue color indicating zero density of states and yellow color a large or maximal density of states. And now one would expect whenever a single particle P crosses a region of very large density of states of the two Magnon continuum, that the phase space for decays is particularly large, and you expect large damping. This can be verified by calculating the spectral function of magnons, and you see indeed in the region where there are a lot of yellow features in the two Magnon continuum, the quasi-particle peak of the magnons are quite blurred out because the lifetime is so short. And at lower energies, you see rather well-defined single Magnon excitations because the decays are rather inefficient. Now we can increase the magnetic field, which changes the single particle spectrum and hence also the two Magnon density of states. And if you have a look at the spectral function on the right-hand side, you see that the damping is not only strongly momentum dependent, but also strongly magnetic field dependent. Now, in principle, these features can be measured within neutron scattering. However, we can also have a look at what happens in microwave absorption experiments, where we now focus on the gamma point of the Brillouin zone. This is shown here in white again, the single particle excitations as a function of magnetic field, and in the background again the two Magnon density of states. And you see again, whenever the single particle peaks cross a region of particularly large density of states, indicated here by the red arrows, you see that the quasiparticle peak is strongly wiped out. Let us now have a look in particular at the three magnetically active modes, the anti-clockwise mode, the breathing mode, and the clockwise mode, which typically can be measured in microwave absorption spectra. And there we see that the anti-clockwise mode is extremely well defined. It's a very sharp quasiparticle peak, in contrast to the breathing mode, which exhibits some damping, but the clockwise mode, we see there's a large field interval over which it is quite strongly damped. And this can be reproduced here again by explicitly plotting the line width of these three modes as a function of magnetic field. You see the clockwise mode, the green curve, has large damping. In contrast, for the breathing mode and the anti-clockwise mode, we had to multiply the damping by a factor 10 or 100 respectively to make this curve visible here on the scale. And such a strong difference cannot be explained only by kinematic arguments, but now we really have to look also at the interaction vertex, which we have done here. At the bottom, you see a lot of towers that tell you something about the efficiency of a particular decay channel. So we are now forgetting about this delta function and are just integrating over all decay processes, only the interaction vertices. And here we look at all the decay channels for the anti-clockwise mode. So the anti-clockwise mode can decay into two other modes, and it is shown here for the 10 energetically lowest modes how large the integrated interaction vertex actually is. So for example, this this green tower tells you that the anti-clockwise mode interacts most strongly with the breathing mode, and the anti-clockwise mode itself probably at a different momentum. The details are not too important. The main take-home message is that for the breathing mode, we see that these towers are already very much larger, approximately by a factor of 10. And if we go to the clockwise mode, these interaction vertices are even larger, which tells you that the clockwise mode is most strongly interacting with all of the other modes, much more so than the anti-clockwise mode. And our results now have two implications. One implication is that there are excellent prospects for topological magnonics and skyrmion crystals, because at low energies we can completely forget about the spontaneous decay because the damping is almost negligible. This is particularly interesting for the anti-clockwise mode, which happens to be topologically non-trivial and stabilize chiral edge states, which is why we argue that as long as you stay at low energies, you should be able to see chiral edge states in skyrmion crystals. And the other take-home message is that out of the three magnetically active modes, the clockwise mode is the least stable. And one could now ask the question if it is possible also in experiment to see this strongly magnetic field dependent damping or line width broadening of the clockwise mode. If we plug in numbers for a thin film of CSO, we find that the quantum damping as compared with the usual Gilbert damping can indeed be 3 or 4 times larger, assuming that the damping is ultra low. So here for this particular numerical estimation, we have been assuming that the Gilbert damping is only 10 to the minus 4. But in principle, we expect that for this ultra clean magnetic insulator, one should be able to see in microwave absorption experiments that the line width should drastically change upon changing the magnetic field. These are the two take-home messages of our work. The clockwise mode is the least stable out of the three magnetically active modes, while the clockwise mode is the most stable. And there are excellent prospects for topological magnonics and skyrmion crystals. For all the details, I would like to refer you to our publication in Physical Review Research, and I thank you very much for your interest in our work.